I promised that we would finish off what we were doing with regression before continuing with classification. Classification is going to be very exciting, but let's just finish what we said. We were describing how we have the dual regression representation, where instead of phi being the weights on our dimensions of x, we were saying that's useful at times, but sometimes maybe we don't have very much training data, x is very high dimensional. Let's instead let the parameters phi focus on which examples, which training examples we should be taking into account when learning. So in this case we were saying, look, I can look at data point x1, data point x2, and make my parameter just based on that. Whatever high dimensional x is sitting behind both these data points, we're not worried. We're just going to use them as a guide for helping us figure out our phi, and our phi is going to be some weighted version, right? These were psi's instead. That we were saying that psi's could be equivalently weighting x1 versus x2 versus all the other x's. So we went through and said, all right, that's the dual linear regression model. We'd previously seen sparse linear regression, where we use what? What kind of distribution? T-distribution. Student T-distribution as our prior parameters, instead of using a big spherical Gaussian for our parameters. So this was encouraging us to just choose a small set of parameters. This was when phi was still the weights of our x dimension. So can you guess what we're going to do here? We're going to combine the best of our sparse linear representation along with our dual representation so that we can make our weights, our psi, which has a direct relationship to phi, make our psi help us choose which training examples, x1 through xi, are important to us. And we're going to use the student T-distribution to help us enforce that we don't have sort of equal weights of all of our training points. So the relevance vector machine is achieving this goal. This is our posterior illustrated probability of W star given X star. Remember, we've got a discriminative model. And we're saying, all right, for all my possible inputs on the x-axis, these are my possible outputs on the w-axis. All the blue dots are training points, but by using a student T-distribution as our prior in the dual representation, in other words, in the representation where we're saying weights should mean how much do I care about each training example, in that representation, we're saying student T-distribution will help us prioritize some dimensions, i.e. some examples more than others, and the big blue dots here are the examples that were emphasized. So here what happened was that only sort of 6 of the training examples were given high weights after the maximum likelihood learning happened. And the other blue dots, they're still here, but basically their weight was insignificant. So their phi parameter, the entries in phi that correspond to those training examples are very small, and they're not contributing much, if at all, to our final representation, which is this color map, this heat map, which is obviously now giving us the ability to do nonlinear regression, right? So we have this pretty nonlinear shape, and in fact, we're only really leveraging 6 main training examples to do that. You don't know that when you're collecting your data, right? You don't know. If you knew, you would just say, oh, I'll just grab the 6 important ones, right, in advance. You don't necessarily know that. You have to have data all over the place. But our goal here was to make this parametric representation of our posterior. And our parametric representation, this equation now, turns out it can basically get away with just weighting these 6 data points. Just like we were showing when we introduced the dual representation, we were just showing just 2 data points, right, x1 and x2. Here, all right, 6 are enough to sort of capture the shape of this regression model. That's relevance vector machines. That is what we were using in the example that I illustrated here with the pose estimation, right? Where we were saying, we've got very high dimensional D. We've got, for our input, we've got 55 dimensional output. Okay, maybe we have 2,000 something training examples in this case, but it turns out that if we use a relevance vector machine, you only need about 6% of those to make your parametric model. And now, at test time, you can get new silhouettes and see how well you're doing. In this case, 6%, 6 degrees average error for each of the joints. I'll just go back very briefly. The relevance vector machine, right? Of course, now we have this situation where we have the student t distribution as our prior on our weights psi, and that has parameters. And so we have this potential problem that we need to update our variances and our hidden variables, because our student t distribution, remember, is this version of Gaussians where we have lots of Gaussians all at the same mean, but with multiple different variances. So we have, again, hidden variables and our parameters, and so we can iterate back and forth EM style to optimize this to do a maximum likelihood solution, for example. All right. So if you're looking at the RVM parameters and you're seeing, okay, these are the update equations for our hidden parameters and our variances, right? I'm going to flash sort of backward to what it looked like when we were doing the sparse linear regression model. And you should see, you should see that they're not very different. What are you seeing changing most between these? Speak up. The D's versus the I's. So our RVM is looking at the weights in terms of the I's, in terms of which training example I is being weighted how, whereas the sparse linear regression model was looking at the D's, the different dimensions D. Okay, and we've already done the applications. So, belated, that's regression. Going to move on to classification now. So we're going to completely different, except, in fact, when we start off, it should look very familiar. All right. So, classification. We're going to try to get through as much of this as possible. I have a particular love for random forests, and hopefully we will get there. So this week we will learn how your face detection algorithms work in your digital cameras, and we will also see how the Microsoft Kinect estimates your pose when it's taking these 2 depth pictures of you, and how it does so real time. So, diving in, logistic regression sounds like regression, but focus on the logistic part. So we're trying to do classification this week. So this is you've already guessed, right? We're trying to say that the world can be separated into a discrete number of bins. Everything falls into a bin. In the case of gender classification, we have 2 bins, right? The world is either in state 0, so we have a male face in front of us in this picture, or the world is state 1, we have a female face in this photo. These could be training examples, these could be test examples. But the task is pretty clear, right? We want to assign a label W equals 0 or W equals 1. All right. We're going to use a discriminative model, just like we did for regression. So what we care about is the probability of the world given our data X. So, if we recall, it's my version, my sort of template version. If you want the probability of something given something and your parameters, right? And here we're saying W and X. Then you're going to have to say, I want my distribution on W to be based on some function of X and my parameters. Right? Now, in regression, we would try linear functions of x, where we used phi's, right? We tried nonlinear functions of x. This isn't going to be shockingly different. So, for our logistic regression classification, right? Remember, focus on the logistic. We're going to say, the distribution that we choose for W is going to be a Bernoulli distribution. Bernoulli distribution is basically this binary distribution that says, okay, we've got sort of a histogram of how likely it is to be W0, how probable it is to be W1, right? And by changing the parameter lambda, we can make one or more or the other more likely, right? If you're flipping coins, hopefully the coin is fair, and so those are equal. So we want to have a Bernoulli distribution. It's going to be fed with our parameters phi0 and the phi vector and our data x, just like we did for regression. And the function sitting inside, so this function here, is going to be the logistic sigmoid function. Logistic sigmoid, I'll show you in just a moment, there'll be a slide, but basically it's the one that maps all the values that could go in between negative infinity and positive infinity into the range 0 to 1. So you're supposed to sort of focus on the right side of that equation, not the left side. All right. So the argument to the logistic sigmoid, A, is called the activation. And we're defining it as phi0 plus the phi vector transpose times x. All right? This shouldn't be too much of a surprise after last week when we did regression, right? I've already explained that the logistic sigmoid is going to, even though A is going to be ending up in this range, that it's going to map it to the range 0 to 1. And the logistic sigmoid equation, if you need to implement it in MATLAB, is 1 over 1 plus the exponential of negative times the activation. All right. So if we illustrate that, we're saying I input a bunch of x's. My activation function, this is a plot of my activation function for different values of x, is just this linear response. Obviously, we see that this could keep going to negative infinity, could keep going to positive infinity. All right, phi0 standard interpretation is the y-intercept, and phi1 is the slope. Higher dimensions, it continues to be the slope of the different dimensions of x. You take this activation, you send it in as your function to your distribution, right? And your Bernoulli distribution for W will say, okay, probability of the world being in state W equals 1 looks like this red function for different values of x. Right? The activation is phi0 plus phi1 times x. So all of this should look, does this look fairly familiar now? Yeah? We haven't done anything too different from our regression model, except that we're now using the Bernoulli distribution, and well, this logistic sigmoid function is sort of convenient. Is already sort of allows us to move from this linear response to something where you can probably see there might be some value in applying a threshold, right, some cutoff. In this case, we're showing both probability of W equals 1 and probability of W equals 0. Normally, we'll just focus on probability of W equals 1, knowing that the other one is the complement. And if you could see this plot for a problem you're working on, you'd probably say, okay, if I'm going to make some decision boundary, some split between where I, for a given input, change my mind from thinking W equals 0 to W equals 1, you might do it so that you maximize your probability, and you're comparing W0 to W1, and you might say, okay, right there is a good split. So the decision boundary we'll come back to very shortly. All right. we have neater notation for regression. Why not have the same kind of neater notation for classification? We simply augment our x vector, our training vector data, or at test time the same thing, by sticking a 1 in front of it. We group together phi 0 and the phi vector, right? Redefine our phi vector to be that combination. And suddenly, hooray, right? Our activation can be written as phi transpose x. Remember, the minus comes with the logistic sigmoid. We didn't have to put it there. Okay? So far, you're looking at me, well, this is all quite dull, right? We're doing very much regression style things. Yeah, I think that's good. You're benefiting from having paid attention to this last week. If you didn't quite get it the first time, hopefully this is helping. You can probably guess what happens when we want to try to do a nonlinear version, right? But we'll come to that. All right, so we now have a neater notation where we're going to remember that the activation A is this phi transpose x. So we're going to worry about learning those parameters phi. If I have a bunch of data points, and this is a way to read this graph, I have an x-axis, I have a univariate input, one-dimensional, and each of these dots is a training example. So the green ones are training examples where the world was in state 0. The magenta ones are the ones where the world was in state 1. And this is how they're distributed along the x-axis. So maybe some low values, green ones have some low values, magenta have some high values. But actually in the middle you see there's a bit of confusion. From both classes we have data points with the same x. All right, so we're plotting here the probability of woman's face given some data input. When we have succeeded in choosing the right parameters phi for our activation, which sits inside of our logistic sigmoid, which sits inside of our Bernoulli distribution on W, right? We will have this probability, this shaped probability. When you look at this, you should think, okay, clearly it goes higher the more to the right we go because there are more magenta, and it goes lower here where there are more green, more of the W equals 0 case. So you could, just eyeballing it, you'd say, well, okay, that's a reasonable fit. And here where the probability is 0.5 is a good place. So we go probability 0.5, dip, 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 and look down and say, all right, that's a good decision boundary for splitting. So if someone comes to you with some data at test time, says, I've got a value of x, you say, well, how big is it? If it's less than this line, if it's left of it, then we'll say that's a male face. If it's greater than that line, we'll say it's a female face. Yeah, with these training examples, we'd be making a mistake. But we've parameterized all our training data. We threw away the training data and just kept the parameters. So this would be chalked up to training error, as with these magenta ones also on the other side of the boundary. Overall, you'd say, well, this model generalizes pretty well. It does a good job in most of the cases. So we can get our parameters phi using maximum likelihood, or we can do Bayesian-derived parameters for our phi. I wanted to remind people, right, that our overall goal, so that you can sort of set this up if someone says, oh, I'd like to estimate my parameters the maximum likelihood way, right, just to remind people, if we're dealing with the probability of the world given x, this is the problem. Someone said, oh, I'd like to use a discriminative model for this, probability of W given x. And you say, well, that's fine. If I don't use a nearest neighbor classifier, I'm going to need some parameters. So we introduce some parameters and we make this joint probability on our training outputs and our parameters conditioned on our training input. And we said that this can be written in two ways, right? One is the probability of, I'm using phi, I'll use phi. Probability of phi given. Anyone want to help me out?
World and X?
Say again?
World and X?
World and X times probability.
The world.
Someone else? Oh, world
given X.
World given X. Okay? Equivalently, I could have written what else instead?
Probability of world given phi and X.
Probability of world given phi and X, and someone else. Probability phi given X. And I'm sorry for the squished version of it. So we had a joint probability here on W and phi. We could equivalently write two equations, and we know that they're both equal to that, equal to each other. Okay. Now, our discriminative model sits inside of this, but we can estimate our parameters by saying, all right, I want to solve for the probability, I want to maximize the probability of phi given W and X. So we're going to move this over here. This is just going to slide into the denominator there. Probability of W given X, right? And now, if I say, all right, this is us learning our parameters, then you can identify very easily, this is the likelihood, that's the prior, right? That's the evidence. So the maximum likelihood way of estimating our parameters, we're going to focus on probability of W given phi and X. For our Bernoulli distribution, the equation is, for a single data point, it'll be lambda to the W sub I times 1 minus lambda to the 1 minus WI. So it's, if the ith training example is a male face, right? So it'll be lambda to the 0, right, times 1 minus lambda to the 1 power. Now, because we're using our logistic regression, our logistic sigmoid function expands lambda into this equation, and 1 minus lambda turns into this, right? And our product, well, we have I training examples. What are we saying when we take the product over all of the training examples? That they're independent. So far, we've just been parroting the fact that they're just independent. In 2 weeks, we will talk about what happens when the data examples are not independent, when they're not drawn independently. For now, we're saying, yep, someone just reaches into a bag. It doesn't matter what order they pull out the examples. They're all independent of each other, but they all represent the same distribution. So we can multiply them all together. All right? What should we do next? We're trying to find the maximum likelihood solution. What's next?
Log it.
We take the log of it. Very good. Why do we take the log?
Because it's easier to sum them all together, and the log is monotonic.
The log is monotonic, so it's not going to change our answer. And it's easier to sum them together, correct? Because here we've got a bunch of these products, pretty messy, hard to work out, hard to isolate, because eventually we're going to want to take the derivative, set that derivative equal to 0, and solve for our parameters, right? For our various parameters, fine. So we take the logarithm. Indeed, our products split apart. That's pretty nice. We take the derivative with respect to phi, and ends up looking like this. So this is pretty good, but it's not great. So there's no closed form solution. Now that we have the derivative of this, and we try to rearrange and get an expression for phi, we don't actually arrive we can't get sort of an isolated version of phi on one side and some closed form equation on the right, like we did with a number of our regression examples. This is really unfortunate. So we don't give up. we have to turn to some kind of numerical nonlinear optimization, which is going to be iterative. So we're going to take steps, one step after another. EM was an example of an iterative algorithm. We're going to use an iterative algorithm to try to find what are the parameters phi that will maximize our likelihood, for our maximum likelihood solution. And I fear that the maximum likelihood solution is actually part of how we will find the Bayesian solution. So you can't just say, oh, no, I'm always going to use the Bayesian solution. No thanks. I fear you will need it. So I want to talk about optimization a bit because it is a big part of fitting parameters for vision problems. We have some parameters that we've been using phi. Okay, sorry, we're going to switch back to theta for a moment. Everybody okay with that, right? We want the maximum likelihood theta that's going to minimize some function of theta. So our goal, our min is saying find the theta that minimizes this and return that. I think we'll come to this later, but we've been talking about maximizing. Minimizing, if you have one equation, you just take the negative of it and use that. So you can either talk about maximizing and use the same algorithm, or minimizing and use the same algorithm. Just change your objective function. So instead of using f, you might use negative f if your intention was to maximize something, and someone hands you code to minimize. All right. So we're going to start with some estimate phi 0. This bracketed sort of this is not an exponent. This indicating at time 0, at sort of step 0, we have an initial guess at our parameters theta, and we're going to take a series of small steps, 1, 2, 3. Maybe we have to take a lot of steps, hopefully not infinitely many, until we find a theta that makes us happy. We're going to try to decrease the cost, right, if we're doing minimization. So we have this energy function, and we hope that every time we make a step, that f of theta gets smaller. Okay. And when we get to a place where we can't step anywhere else in parameter space, then we stop. Now, I try to sort of bring it to life, and I really do think of it this way in my head, that we're now walking around in parameter space. So you can think of the parameter being one-dimensional. I like to think of it as being sort of two-dimensional, like I'm standing somewhere on a mountain range and I'm walking in various directions, and the ground underneath me is going up or down, depending on what the energy function does at that combination of theta. All right. In the one-dimensional case, right, so we have theta varies, goes infinitely far this way, or maybe not, maybe it's bounded, fine. If we start off at some guess of theta and we take a bunch of steps, we might end up down here after infinitely many steps. Our strategy for taking steps, this is what we're going to be talking about in the next few slides. Maybe it's not so clever. Maybe we're bouncing around, always going down, though, and if we're always going down, we'll always end up down here. So that's good. If, however, our objective function that we're trying to evaluate is this funny shape like we have here, then depending on your initial guess at theta, you might start out up here, and then when you slide down, you work your way, hop, 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 and you end up here, and you say, look, I've found the optimum, right? I can't get a lower energy function by changing my theta. I must be done. Well, you found a local minimum. Now, unfortunately, no one hands you this picture of it, so you don't actually know whether your optimum is a local or a global optimum. In this case, this would be the global. Yes?
But we basically just did this problem because in the slide before that we said that every step has to decrease the value.
Yeah.
Which is kind of a guarantee for local minima. So why do we have this restriction?
Well, you're allowed to invent new algorithms for optimization, and indeed people have algorithms where they say, okay, I'm going to drop a particle, which is more like sort of I'm going to run my algorithm multiple times, right? And I'm going to seed it in a number of different initial locations on the theta. Maybe sampling densely. I'll sample every 5 centimeters on this representation of the theta line, and I'll run the algorithm in parallel 100 times and see who converges to the lowest objective function. You're suggesting, oh, well, you can have it that your algorithm accepts choices of theta that decrease the energy function, but occasionally allows an increase. Okay, you're allowed to do that. There are such algorithms. They're a little tricky because, I guess depends on your bookkeeping then, right? It becomes a question of, do you keep track of your lowest one and then allow it to sort of keep hopping? You might inadvertently, if things are like that, that's great. If things are, let's see, like that, you might skip over, the optimum because, well, you decided to go with something that was increasing the cost. So, if you know what shapes are allowed by your energy function, and that's quite valuable information. We've been very careful so far to keep to problems where we could solve in closed form, or we knew that it was well behaved. I'll describe that in a minute. Then life becomes a little easier. If you know that you are expecting sharp, jagged things and lots of local minima, you would take maybe a slightly different strategy.
So, do we take this iterative process because it's often not possible to solve these analytically?
That's right. So the maximum likelihood, so let's keep track of where we are. We're doing a lot of things similar to regression. We have a function, right, that is, I rewrite the function. We've got our logistic sigmoid function applied to our phi multiplied by our x, and we're trying to do classification. But we don't know how to optimize the parameters, and indeed, when we took the derivative, even though we were able to simplify it, we weren't able to pull out the phi's on one side and have a closed form solution for what is the maximum likelihood phi given a bunch of training examples. So that's the situation we find ourselves in now and for much of this chapter. Okay. So things aren't always so bleak. Sometimes you might have an objective function that looks like this. It's a nice bowl. So this is called the convex objective function. In it, if you follow the strategy of always accepting thetas that give you a lower energy function, then you might zigzag until you end up down here. You could do all kinds of searches. You could do kind of a dense search, and we'll talk about a line search. But you will end up here kind of no matter what, even if you don't have a nice closed form equation for this function. So convexity is really valuable. Say, well, okay, I've got the equation for my situation. How can I evaluate whether this function is convex or not? So if it's one-dimensional like this, so it's a function of a univariate theta, then you can look at the second derivative. If the second derivative is always increasing as you sweep across your thetas, then you're in good shape. You're convex. In higher dimensions, you would have to look at your. Let me write this up. In higher dimensions, you would have to look at your second derivative, which we'll talk about in just a moment, and you'll want the Hessian, the second derivative matrix A, to always return a positive value for any non-zero input x. So that would make it positive definite. So here we're looking for a second derivative that's positive in one dimension, and for multiple dimensions, we're looking for a Hessian, a matrix here. So where the second derivative, but in matrix form, is positive definite. So these are conditions that are further described in the appendix of the book. We're going to keep going, and we'll use the second derivative. We'll calculate it right in front of your eyes when needed. All right, so our situation here, just to remind ourselves, we've got this likelihood equation. We want to find the phi's that maximize it. If someone magically computed for us, we said we took the derivative, but we couldn't find the closed form, okay? But if someone went ahead and computed for all phi zeros and phi 1 combinations, what is the probability of phi given all of our training data? This is the map we would get. When we took the log of that, we ended up with this sort of heat map. All right, so what does it look like when we apply our iterative optimization and choose a starting point, bang, and we say, all right, let's now iterate and walk towards a combination of phi's, phi 0, phi 1. We're going to try to walk towards a combination of these two that, in this case, maximizes our probability, right? So we can just take the negative of the objective function, and now we're maximizing instead of minimizing, but it's the same algorithm. So what we're going to see is that we're going to walk from here to here in the first step, and then the second step we'll walk from there to there. And that peak is obviously higher than that, which is higher than that. So by maximizing the log likelihood, we're still going to end up at the peak of the original distribution. So that's good, right? This is our maximum likelihood. And we can even visualize what this looks like back in the domain of inputs x and outputs w, right? Probability of a woman's face on the y-axis. So given our training examples for men, training examples for women, right? When we had guessed this location in parameter space, that parameter space location corresponded to some logistic sigmoid shape, right? This is an activation inside of the logistic sigmoid. This is this right here. Yes. And so the first one has a logistic sigmoid that looks like this. Doesn't fit the data very well because remember this is probability of woman's face, so probability that W equals 1. By the second iteration, we've moved to this blue line, right? That's already better. It's better mapping. It's saying, okay, you know what? Low values of x are less likely to be W equals 1. High values of x more likely to be woman's face. And by the third iteration, right, we've settled in and we said, all right, that's a good logistic sigmoid, i.e. the activation based on phi is as good as we can expect to get it. All right. So how do we do those optimizations? Those how do we go from step 1, from location 1 to 2 to 3? All right. So you can picture this space. This is a two-dimensional space, or my height field where I'm standing in a place. I don't know if it's high or low, but I'm trying to choose where to go next. In this game, I am going to be looking only locally. I can't make evaluations everywhere. I can't sort of look around very easily. So I'm just evaluating locally where I'm standing, and I'm saying, boy, from here, where I am, where should I step next? So in this case, sort of looking in this local neighborhood, which direction should we step into next? So the direction is going to be this vector S. What direction should we step to? So picking a direction, once I've picked a direction, I also will have to pick how far of a step to make. Because if I make a big step, that will be good. I'll be making good progress, hopefully, but I don't want to make such a big step that I overshoot, that I step over what is a good combination of parameters. All right, so for that we'll be using line search. So I'll get to line search in a moment. First, let's focus on this S. How do we find a good S? By the way, if we find a good S and a lambda. This is just a scalar. It's telling us how big of a step to make. We're going to add those on to our existing theta, our theta at sort of iteration t. And then at the new iteration, that'll be theta t plus 1 will be just that combination. So our goal right now will be to find s and lambda that maximize or minimize our objective function. So you're standing somewhere and you're looking around and saying, I want to find, let's see, the minimum, right? So you're standing on a hillside, you look around and you say, well, if I want to quickly get to the bottom, to the local minimum, which is all I can hope for, I'm going to find the direction where the slope is the steepest, and I'll choose that direction. That'll be the direction I go. So we start off here in blue and we say, well, okay, the steepest direction is sort of pointing that way. So let's take a step, lambda long. We'll talk about how to choose lambda, but we'll take a step and go in that direction. So leave for now, just believe me, we'll talk about how to choose lambda. For now, we're just picking the steepest direction of descent, taking a step there, and then repeating the process. Step again, search for direction, step, search for direction, step. And after 5 iterations, we end up here. So this is great, right? If I can tell you how to choose the direction and how to choose the step length lambda, then we're basically in business. So if we have trouble computing the gradient because we don't have a function, so someone hands you a nice equation, great, you can take the derivative of it. So just do that. Partial of f with respect to each of the different elements in phi vector. If you don't have an equation, or it's not differentiable for some reason, then you can use finite differences. Finite differences is basically just saying, all right, keep your foot at your starting location, but maybe just put a toe down in sort of one direction. That'll be a unit vector in x, and maybe another unit vector in y. But first, let's just do the x. We'll take a very minimal step. That's me putting my toe out just in the slight direction of unit vector ej, and I'll calculate the function there. I'll just put my toe out and see, is that higher or lower than where I am now, and by how much? I compare that to where I am now, and that difference is how much. Normalize it by a, right? If I suck my toe out a lot or a little, this will take care of it. And now, when I do this with respect to direction j equals x, or j equals y, or if I have many dimensions, now I have a version, an approximation for how much is the slope changing compared to where I am now. Locally, I know, okay, it's changing, it's going downhill there, maybe going uphill there, but it's going even further downhill straight ahead. Or because you have the x and the y component, you can calculate in between if there's a gradient direction that's even stronger. So whether you have f or not, we can compute some kind of gradient, first derivative meaning slope, really, right? Just think of it literally as slope. How much is the energy function f changing for each of the dimensions of our theta vector? All right. So I showed you an example where it converged in 5 steps, and that's wonderful. It might be also that you take more steps to converge. It still will converge, but we start, let's say, here, and we do what we've just said. We pick a direction where the gradient is changing a lot, and take a step in that direction, look around, pick a direction where the gradient is changing a lot, and we zigzag, zigzag, zigzag quite a lot here. This was blown up here, until eventually we find our way here. So these last steps are quite big, and that's good. We're making very fast progress there. These steps were all very slow. So what was happening there? Well, it started in some location, and basically you see this kind of valley, right? The whole valley is tilted downward. It's pointing towards the the bottom there. But we're bouncing off the sides of the valley, right? We keep running across and missing sort of the minimal line that would go through here. So the search for a good direction and a good step size, if you are just using regular steepest gradient descent, could leave you zigzagging quite a long time before you eventually sort of get to the bottom of the valley and can continue on your way.
Why would you stop at 22? Is it just till it stops moving completely? Because it's quite close to not moving at the beginning.
Yeah, so this is very dangerous, right? You say, okay, typical for these types of algorithms is you define two thresholds. You say, I have one threshold, which is a maximum number of iterations that I'm willing to tolerate, because I don't want this thing to run for 3 days and then not know if I should shut it down or get it running for another minute. So I'll say, okay, I'll give you 1,000 iterations budget, and I'll also define an epsilon for how much of an improvement in the energy function is negligible, right? If for some number of steps you keep coming up with negligible improvements in the energy function, I give up. That's it. You're basically at some minimum, and I'm not going to bother. If you choose that epsilon if you make it too small, you might think, you know what, my energy function is just not improving very much. Let's abort here, right? Which would be tragic, right? Because you didn't get to the place where you could see the easy way down to the minimum. All right.
Isn't this support mainly used for attenuation or something? Heating down?
This is you're thinking of.
In big steps in the beginning.
Yeah, you can schedule the steps to be different sizes. So I think this is kind of what we're not covering that very much. But yes, there are simulated annealing algorithms which sort of control the step size. We're going to do line search for today and for the lab this week, which is not so clever, but it's easy to implement. Okay. So we've got a problem that our first derivative, which is me sticking my toe out or me actually calculating the first derivative, is just telling me which way is the gradient going. The second derivative is here to the rescue. The second derivative is the slope of the slope, or the rate of change of the slope. So it's saying, you know what, I know that the mountain range is going that way, but when I compute how fast it's changing, the second derivative of that slope, I can see that it is changing. It is now changing quite slowly. So maybe I should be making a very small step here, right? Whereas if you're in this area, you might say, you know what? I know that things are. Let's see, we're here. Let's say I know that things are slanted to the right, but the slope is very gradual, right? And a gradual slope means I can probably afford to take a bigger step, right? Should go further. So we're hoping, with second derivative, we're hoping that the energy function is somewhat smooth, right? That if it feels like it's a gradual change, then it will stay gradual for a while. And what you're seeing here is that you can also fit a parabola to your second derivative. Okay, so second derivative is going to be used as an indicator of whether we should be taking big steps or little steps. All right. So this is where Newton's method comes in. Newton's method takes advantage of the second derivative. Here what we're doing is we're saying, all right, I have some ideal theta. I wish to reach this theta. What is the true theta? Well, I don't know exactly, but I'm going to approximate it with a Taylor expansion. So if you don't remember your Taylor series expansions, that's okay. The point is that you start off with some initial guess of theta. You know that there's some difference between your initial guess and the optimal theta, and you multiply that by the first derivative with basically a weight of 1, and then you have a weight of 1/2 of the same difference times the second derivative. And if you did the Taylor series expansion all the way out, right, you would see these coefficients are getting smaller, right? And these derivatives are getting higher and higher order, right? You're saying, oh, I'm going to look at the curve, the rate of change of the rate of change of the rate of change of the energy function and so on. But for our purposes, Newton's method just truncates it at the second derivative and says, okay, we don't care about those other parameters that we would have out here. We just take first the initial guess, the first derivative and the second derivative, take derivative, set it equal to 0, rearrange so that we say, all right, theta hat equals this equation, which is a function of basically the first derivative divided by the second derivative. And we're just subtracting that off from our initial guess. It's saying, essentially, I've got two directions I can go in on this mountain range. If one of them is maybe, they're both going down, but one of them is going down at a faster rate, right? Then I'll take a bigger step that way and a smaller step in the one that's going at a faster rate. So, this way we have our estimate for our theta hat. And now we're going to do a line search. We're going to say, wait, hold on, how big should my step be exactly, right? We've just sort of said, well, these will be these weights. Lambda is going to be applied, and how do we choose lambda? All right, so we have this matrix of second derivatives. It's called the Hessian. The Hessian, I already mentioned, is this thing that is positive definite if it obeys this equation. That would mean that it's convex. So that's good. That means when you get to a local minimum, you would say, oh, this is actually the global minimum. Great. All right. The second derivative can be expensive to compute with finite differences because you have to compute you have to stick your toe out in the x direction and then sort of again in the x with respect to the x and the y. So you have to do these sort of more combinations of calculations. But remember that we're using the second derivative as an indicator for how big lambda should be. So if we just do steepest descent, right, we might start here and work our way to a solution in 5 iterations. That's great. Newton's method does the same thing as steepest descent, maybe even fewer iterations. But okay, pretty much similar behavior. If you start at a different location, though, steepest descent, this was this pathological case of zigzagging back and forth across the valley, whereas Newton's method is going to say, oh, right, I'm using the second derivative as well. It improves our choice of direction so that we can get to the same answer in 4 iterations. So Newton's method, you pay the price, you have to take second derivative, but you get your solution more quickly and more reliably. All right, last slide, line search. How big should your step be? You've picked a direction, you're going in that direction, you're trying to decide how big should your step be. You start off and you say, I have a lower limit and an upper limit, A and D. I know that my parameter value, my step length is going to be somewhere between A and D. All right, and you subdivide the range between A and D. You just say, all right, subdivide them. We can do it equally. I'm going to make a B and a C. I'm going to evaluate the function, my energy function at B, my energy function at C. If one of them is going to be higher than the other, energy at B and the energy at C are not equal, whichever one is higher, I'm going to clip that part off. So I'm going to say, look, energy at B is higher, so I'm going to clip off everything between A and B. I'm going to move A inwards, put it here, leave D here, and I'm going to repartition this space with a new B and a new C. And repeat. Evaluate your energy function at B and C. Remember, well, it doesn't matter. We evaluate at B and C. Pick which one is higher. Oh, C is higher. Clearly, things are getting worse, more expensive that way. So clip everything to the right of C. Right? Move D in, repartition, and repeat. Hopefully, eventually, right, you'll find that you put a B here, and it gets very hard to find a better energy function estimate or better theta that gives you a lower energy, and you will choose that as your lambda step. Okay, that's it. We started with this. The idea is that we're going to be estimating our maximum likelihood parameters by doing Newton's method and line search. All right. Final slide. Really, when you do this, right, you get the partitioning that I already showed you. Or in 2D, we might do it this way, where we say, okay, negative training examples, positive training examples. Here is this straight line representing the partition. Good, we'll pick up there on Thursday. Thank you.